Let me start us with this, because it was brought up yesterday, but I don't think I did a great job in this class of being careful about the way I presented it. At one point or another, we had something that looked like this. Does this ring a bell from yesterday? I know it was so very long ago, and I know that your memory isn't what it used to be because you're getting older now. So we know I didn't make this clear, and I need to. The change in potential energy from going from one place to another would look something like this. Now, one of the first things I did yesterday after we got here, and I didn't distribute like this. I left it like this yesterday and then said, well, what if our starting point was infinitely far away? Remember me saying that? And then I immediately said we can just get rid of this term because 1 over infinity would be 0. I don't know how many of you know that already. So look, if you didn't know that already because you don't remember it from math or whatever, you should put in your notes because you could be asked something like that on the exam. Not about gravity, but just what happens if this number is really, really big. You should say it goes to 0. So if Ri is really, really big, we're saying that that term goes to 0. They can say that about anything in any equation that we've talked about, where there's something in the numerator or the denominator asking about the limits of what the value would be under certain conditions. So the condition of setting one number to infinity happens a lot. So be prepared to answer that question regardless of which thing we happen to be discussing or studying at the time. Now, that essentially wiped out this term, right? Setting that term to 0. And what I said to you at that time was, well, that means we can just state that not the change in potential energy, but the absolute potential energy for an object near another object looks like this. Now, there's a lot of implications about this that are kind of academic but not reality. So let me give you an academic but not reality kind of approach. One of the things that we have to do in E&M as a matter of course is talk about the energy associated with a system of particles. And we often talk about the structure of the atom when having that conversation. I'm supposed to have that conversation with you guys, but it's a little more complicated in that talking about a system of objects in space can't exist without the fact that there's lots of other objects already there. We can't create a box that has no universe in it and put something in there and say, this is the first object in the universe. Now, the reason we can do it in E&M and talk about it is because atoms are relatively small compared to their environment, and they can be very much isolated from their environment in a way that gravity can't. Because gravity is so much weaker a force than the electrostatic force, you really need to get rid of all other objects around you to be able to study it by itself. So we don't. But there is the academic questions surrounding gravity that tend to go like this. How much energy is there when you place a single object in space? And say it has mass m. Well, the answer is none. It takes no energy to put the first object in space because there was nothing for it to interact with. So placing the first object there costs you nothing. We only start having energy if 1, there's motion, or 2, there's another object with which to interact through a force. I'll say that again. Energy only exists in 2 places for us. The first is in motion. So if something's moving, it has energy, period. But the other way something has energy is if it interacts with another object through a force. So in the past, I have never, in front of a group of students, asked how much gravitational energy there was for a single object to be in space. But our curriculum is a little more modified this year, so I'm making sure I walk down this road and at least in a cursory way talk about putting the first object in space costs you nothing because there's nothing there for it to interact with. However, the second object, the moment I want to move a second object into space, so now this is M2, and we'll call this M1. The second object has something to interact with, and these two objects together now have potential energy. The potential energy they have can be summed up in this statement. All I need to know is how far apart the two objects are from each other in order to determine the amount of potential energy that exists between them. Now, this is going to be a negative amount because it's explicitly negative because of the way we chose our reference point. Now, with two objects, it's no big deal. But when we bring the third object in, the third object changes the ante a bit because the third object has two other objects in which to interact. Now, introducing the third object in this example, we can figure out the energy, but only for a static situation like this where they're all fixed in place. So I can't tell you about what they're going to do really. I can get a hint at it. I know they're probably all going to be kind of pulled together, but depending on their masses, some might be traveling faster than others. Who knows what's really going to happen? But to figure out the energy, I now have to realize that this is R12, representing the distance between mass 1 and mass 2. There's now a R23, which is the distance between mass 2 and mass 3. And then there's a R13, which is the distance between mass 1 and mass 3. So although it didn't cost me anything to deal with the first particle, and only cost me this amount of energy to deal with the second particle, as long as I put a 1, 2 here, there's now the potential energy associated between mass 1, mass 3, and a potential energy associated with mass 2 and mass 3. If I want to know the total potential energy of this system, I'd have to sum all three of these up. And that would be the total potential energy of this system. And yes, it's negative. This would be how much energy I would have to add to the system to separate them, to get them apart. So you can imagine, if I add a fourth one, what's going to happen? And a fifth one, what's going to happen? Every time I add another particle, it interacts with all the particles that are already there. So the total energy can only be calculated by breaking this problem up into multiple two-body problems and finding the energy for the two bodies at a time. Now, I think this is a very unlikely question to ask because, again, what are we doing? Holding three objects in place just to see how much energy there is? But it's not impossible. So, okay so far? Go ahead. Is to say, if I have two masses, M1 and M2, and I place them a distance r apart, how much energy would be required to separate them? So I already gave you the answer to this. The amount of energy required to separate them would be the amount of energy necessary to bring their gravitational potential energy up to 0. So I would have to add whatever kinetic energy would bring the system to 0. This is different than what I talked about yesterday, because what I talked about yesterday was talking about the Earth staying in place and us sending Simon off the planet to a place where he wouldn't be able to come back. but I wouldn't want to do that. I want Simon as part of this planet. It's good to have a Simon among us. Hi, Simon. If I wanted to ask how much energy is required to send these two objects away or separate them, then I'd have to give them both energy. So we'd have 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And this would sum to be 0. Now, obviously, we don't know which object would get more of the energy. And it doesn't really matter as long as combined they have enough energy so that their velocities send them apart. Well, they'd have to have enough kinetic energy to overcome the amount of potential energy that's in the system. Now, let's say we do this by blowing something up between them. And I use that, you can put a spring between them if you'd like. But, in space and stuff, blowing something up seems to be the way to go. That's how we put rockets out in orbit and stuff like that. So igniting something makes more sense. So we're going to initiate something that will give the two things energy. So if you want to think of it as a spring, fine. If you want to think of it as an explosion, fine. It doesn't matter. What does matter is the consideration that this problem would still obey the rules of momentum. And if the two objects were at rest before we added the energy, then the momentum of the system would be the same after we added the energy. This would still have to obey conservation of momentum. So although this is true, this would also have to be true. So if the momentum of the system was 0 before, the momentum of the system would remain 0 afterwards. I bring this example up because this is a realistic problem that you could be asked to portray. It has all the qualities of things we've talked about in the class. And the difference is this problem is one we've nearly done before. We've had a problem of two masses on a table and a spring between them. And we said, well, if we release the spring, how fast does each object go? Well, we're saying the same thing. We're saying there's a certain amount of energy associated with their gravitational attraction. And we gave them, through some means, an explosion or something, enough kinetic energy to escape. Well, what would be the velocity of each of the objects? Well, part of that would come from kinetic energy, part of that would come from momentum. Together, we'd create two relationships with two unknowns. The velocities would be the unknowns. We could use this to calculate how fast each object would go according to the amount of energy released. So if we release enough energy to separate them, it doesn't mean they're both going the same speed. It would probably mean that the bigger one would be going slower than the smaller one. And by proportion, the smaller one and bigger one would be able to get far enough apart in order for them to come to rest infinitely far away. It's a thought experiment. It's not a real thing that you can do because we can't put just two objects in the universe by themselves. So again, it's just a thought experiment. But we use these to try and get an idea for modeling the universe. So for us, the two-body problem is the limit of our capabilities. But this is a reasonable two-body problem. Now, I'd rather talk about actual, more real-life things than this fake idea of blowing apart two masses and seeing where they go. So I'm going to end my conversation about this as this is a thought idea, but let's talk about what we really are going to need to be able to understand. I will have one or two practices like that for you to just see how the math would work, but they're going to be messy. Just be prepared for that. When I say messy is there's no way for me to make those numbers work out really nice. So you will probably have, really difficult numbers. I don't want to talk about any specific system, but I do want to talk about a planet and a moon for just a minute, and let's talk about a circular planet. I'm sorry, a circular orbit that's that's being had by this moon. Does that make sense? I kind of stumbled over my words there. So we were talking about a circular orbit. And let's say that MP represents the mass of the planet and MS represents the mass of the satellite or the moon. Let's also indicate that they are separated by a distance, capital R. This is the distance from the center of the planet to the center of the moon. You guys have done this question before, so I'm going to ask you to do it again. Can you set up a net force relationship that could be used to figure out the velocity of the satellite? This was first semester. I know I'm asking a lot of you to remember this class, but it's probably in your notes. If you brought them, it would have been something about orbits. I didn't ask you to solve for the velocity. All I asked for you to do was set up a relationship that could be used to find the velocity. I'll give 60 seconds, and then I'll pick on my favorite, kicking posts out there.
Mass of the satellite times the gravitational constant over r squared is equal to the mass of the satellite times v squared over r.
Thank you. So Corbin did net force equals MAC. That's where I wanted you to start. Now, I was purposeful in what I wanted. I didn't need you to solve this for V because I want to show you something that is a little more interesting or valuable to this discussion. The system has a certain amount of energy, and the energy of this system is a combination of its potential energy and its kinetic energy. Right? We know the planet has a certain amount of kinetic energy, but it also has gravitational potential energy because it's located near another planet. So if we're interested in figuring out the total energy of the system, it's going to have to be, minus MP MSG over R. That's the gravitational potential energy of the system. But it's also going to have kinetic energy of 1/2 ms v squared if we're only talking about the kinetic energy of the satellite. The planet might have its own kinetic energy, but we're just talking about the satellite planet system. Is that okay so far? Nothing crazy? I'm just adding up potential energy and kinetic energy. The thing is, you do notice that the kinetic energy of the satellite contains ms v squared, right? We could probably put this in terms of the kinetic energy if we'd like. Right? It's already got an ms and a v squared. So it wouldn't be hard to make this look like kinetic energy, would it? Let's get rid of the one r that's on both sides. Shall we do that? So if I do that, I'll get MP MSG over R equals ms v squared. Now, what would I have to do to make the right side look like kinetic energy? Multiply by 1/2. Perfect. So I can't do something on one side of an equation without doing it on the other side of the equation, right? So let's multiply both sides of this equation by 1/2. And suddenly this is the kinetic energy of the system, which means this is the kinetic energy of the system. I want you to notice right away that the kinetic energy is equal to something that looks a lot like the information related to potential energy. Do you guys agree? Except it's positive, because kinetic energy would always be positive. So the total energy of the system could be written as negative MP MSG over R plus MP MSG over 2R. Now, do you see that we could add these two things together if we got common denominators? So I'm going to get common denominators. All right, multiply top and bottom of the left one by 2. And now I have 2r as my denominator. Is that okay, Cami? I'm sorry, it's messy. Rating my handwriting, fine. Is that better for you?
Yeah.
Well, you know, I do live my whole life hoping I can make things better for Cami. So, when we add this up, I hope you realize that we'll get a negative MP MSG over 2R. There's two things I need to point out here. First, this is always going to be true for objects in a circular orbit. Like, this has to be. And this relationship isn't arbitrary. It's a consequence of the fact that the force and the gravitational potential energy are related. But what's also interesting here is that it's clearly still negative, right? So it is inherently negative because the object is still trapped, right? It does not have enough energy to escape, but it is moving. It's not falling into the planet any longer, but it is not escaping either. So things that are trapped in orbit still do not have enough energy to escape the orbit. Even if they're moving really fast, they don't have enough energy to get away. So things are stuck in the gravity well, regardless of what the orbit looks like. Now, our next conversation, which we clearly will not get to today, but we do need to get to, is to talk about orbits that are no longer just circular. We're not going to be able to finish this today, but there are a lot of qualities of elliptical orbits that we can study that we need to study.